Hello and welcome to Earth Science Lecture 4, the Rock Cycle and Igneous Rocks. So, why study rocks? All Earth processes depend in some way on the properties of these basic Earth materials. Events such as volcanic eruptions, mountain building, weathering, erosion, and even earthquakes involve both rocks and minerals. Consequently, a basic knowledge of Earth materials is essential to understanding the most of our geologic phenomena that we'll be talking about in our upcoming lectures. Every rock contains clues about the environment in which it formed. For example, some rocks are composed entirely of small fragments of marine organisms, which tells Earth scientists that the rock likely originated in a shallow marine environment. Other rocks contain clues indicating that they formed from a volcanic eruption or deep in the earth during mountain building. Thus, rocks contain a wealth of information about events that have occurred over Earth's long history. The rock cycle. This is a model that illustrates the origin of the three basic rock types and the interrelatedness of Earth materials and processes. The rock cycle allows us to see many of the interactions among the components and processes of the Earth system. It helps us understand the origins of igneous, sedimentary, and metamorphic rocks and how these rocks are connected. In addition, the rock cycle demonstrates that any rock type, given the right circumstances or sequence of events, can be transformed into any other type. Note that this lecture is titled The Rock Cycle and Igneous Rocks, so we're only going to cover one of the three types of rocks in this lecture. The other two will be covered in our next two lectures. So this is our basic rock cycle. If we follow the purple arrows, that's the basic cycle, and then the whiter or blue arrows in the middle indicate some of the more uncommon processes that occur. But in general, we start with a magma pool that solidifies to give us our igneous rock. That gets broken down and gives us sedimentary rock after compaction, and then we get some metamorphic rock. So this slide right here is mostly going to be a reference for you. In the coming slides, we will discuss each of these parts in detail. So let's take a look a little bit deeper. Let's begin the journey in our rock cycle from the very beginning. We begin this discussion with molten rock, which is called magma, which forms by melting that occurs primarily within Earth's crust and upper mantle. Once formed, a magma body rises toward the surface because it is less dense than the surrounding rock. If magma happens to reach the surface of the Earth and erupts, then we would call it lava. So that's the only difference between magma and lava. Magma is inside the Earth, lava is on the surface. Eventually, molten rock cools and solidifies in a process called crystallization or solidification. Molten rock may solidify either beneath the surface or, following a volcanic eruption, at the surface. In either situation, the resulting rocks are called igneous rocks. If igneous rocks are exposed at the surface, they will undergo what we call weathering. That is, the slow disintegration and decomposition of rocks by the daily influences of the atmosphere. The loose materials that result are often moved downslope due to gravity and are then picked up and transported by one of the following erosion agents, that being either running water, glaciers, wind, or waves. These rock particles are dissolved substances called sediment and are eventually deposited. Although most sediments ultimately come to rest in the ocean, other sites of deposition include river floodplains, desert basins, lakes, inland seas, and even sand dunes. Next, the sediments will undergo a process known as lithification, which is a term meaning conversion into rock. Sediment is usually lithified into sedimentary rock when compacted by the weight of overlying materials or when cemented by percolating groundwater that fills the pores with mineral matter. If the resulting sedimentary rock becomes deeply buried or is involved in the dynamics of mountain building, it will then be subjected to great pressures and intense heat. The sedimentary rock may react to the changing environment by turning into the third type of rock, known as metamorphic rock. If metamorphic rock is subjected to still higher temperatures, it may melt, creating magma and renewing the cycle once again. Although rocks may appear to be stable, unchanging masses, the rock cycle shows that they are very much not. The changes, however, take time, sometimes millions to even billions of years. In addition, different locations on Earth are at different stages of the rock cycle. Today, new magma is forming under the islands of Hawaii, whereas the rocks that comprise the Colorado Rockies are being worn down and weathered by erosion. Some of this weathered debris will eventually be carried to the Gulf of Mexico, where it will add to the already substantial mass of sediments that has accumulated there. Other paths are also possible. For example, rather than being exposed to weathering and erosion at Earth's surface, igneous rocks may remain deeply buried. Eventually, these masses may be subjected to the strong compressional forces and high temperatures associated with mountain building. When this occurs, they are transformed directly into metamorphic rock. Uplifting and erosion may bring even deeply buried rocks of any type to the surface. When this happens, the material is attacked and weathered by processes that turn it into raw new materials for the sedimentary rocks. So what drives the rock cycle? Well, Earth's interior heat is responsible for the processes that form igneous rock and metamorphic rock. Weathering and the transport of weathered materials are external processes powered by energy from the sun. External processes produce the sedimentary rocks. So in general, we follow the purple arrows, but now we know that there are alternative paths that are possible, and we know what drives this. It's heat from either the Earth or the sun. So, igneous rocks form as magma or lava cools and crystallizes. Magma is most often generated by melting of rock in Earth's mantle, although some magma originates from the melting of crustal rock as well. Once formed, a magma body buoyantly rises toward the surface because it is less dense than its surrounding rock. When magma reaches the surface, it's called lava. So that's just a bit of review. Molten rock may solidify at depth, or it may solidify on Earth's surface. When molten rock solidifies at the surface, the resulting igneous rocks are classified as extrusive, or volcanic rocks, after the Roman fire god Vulcan. Extrusive igneous rocks are abundant in western portions of the Americas, including the volcanic cones of the Cascade Range and the extensive lava flows of the Columbia Plateau. In addition, many oceanic islands, including the Hawaiian Islands, are composed almost entirely of volcanic igneous rock. Most magma loses its mobility before reaching Earth's surface, and eventually solidifies deep below the surface. When magma solidifies at depth, it forms igneous rocks known as intrusive rocks, or plutonic rocks, named after Pluto, the god of the underworld, in classical mythology. Intrusive igneous rocks remain at depth unless portions of the crust are uplifted and the overlying rocks are stripped away by erosion. Exposures of intrusive igneous rocks occur in many places, including Mount Washington, New Hampshire, including Mount Washington, New Hampshire, Stone Mountain, Georgia, Yosemite National Park in California, and even Mount Rushmore in South Dakota, which you can see pictured in the bottom right. This memorial carved into intrusive igneous rock granite along this surface of the mountain. The massive igneous body cooled very slowly at depth and has since been uplifted so that the overlying rocks were stripped away by erosion. So this rock formation was actually inside the Earth at some point, and it was just pushed up, and then everything around it was eroded away. So magma is molten rock composed of ions of the elements found in silicate minerals, mainly silicon and oxygen, that move around freely. Magma also contains gases, particularly water vapor, that are confined within the magma body by the weight and pressure of the overlying rock, and it may contain some solids, such as mineral crystals. As magma cools, the once mobile ions begin to arrange themselves into orderly patterns, which is a process known as crystallization. As cooling continues, numerous small crystals develop, and ions are systematically added to these centers of crystal growth. When the crystals grow large enough for their edges to meet, their growth ceases. Eventually, all the liquid melt is transformed into a solid mass of interlocking crystals. The rate of cooling strongly influences crystal size. If magma cools very slowly, ions can migrate over great distances. Consequently, slow cooling results in the formation of fewer but larger crystals. On the other hand, if cooling is relatively rapid, the ions lose their motion and quickly combine. The result is that you get large numbers of tiny crystals that all compete for the available ions. Therefore, rapid cooling results in the formation of a solid mass of intergrown crystals. If the molten material is quenched or cooled almost instantly, there is insufficient enough time for the ions to arrange themselves into a crystal network. Solids produced in this manner consist of ions distributed somewhat randomly. Such rocks are often termed glass and are quite similar to ordinary manufactured glass. Instant quenching often occurs during volcanic eruptions that produce tiny shards of glass called volcanic ash. Igneous rocks are composed mainly of silicate minerals. Remember from our mineral lecture that silica is just SiO2, silicon and oxygen. Chemical analysis shows that silicon and oxygen, usually expressed again as SiO2, the content of magma, are by far the most abundant constituents of igneous rock. These two elements, plus the ions of aluminum, calcium, sodium, potassium, magnesium, and iron, make up roughly 98% by weight of the magmas. As magma cools and solidifies, these elements combine to form two major groups of silicate minerals. The dark silicates, which are rich in iron and/or magnesium and are comparatively low in silica. Olivine, pyroxene, amphibole, and biotite mica are the common dark silicate minerals of Earth's crust, as discussed in the previous lecture. By contrast, the light silicates contain greater amounts of potassium, sodium, and calcium and are richer in silica than the dark silicates. Light silicate minerals include quartz, muscovite mica, and the most abundant mineral group, the feldspars. Feldspars, if you recall, make up at least 40% of most igneous rock. Despite the great compositional diversity, igneous rocks and the magmas from which they form can be divided into broad groups according to their proportions of light and dark minerals. Near one end of the continuum are rocks composed almost entirely of light-colored silicates, quartz and potassium feldspar. That's on the left on the figure. Igneous rocks in which these are the dominant minerals have what we call a granitic composition. So if our minerals are mostly made of the light colors and of feldspar and quartz, we consider its composition to be granitic or felsic. So these are often termed felsic, which is a term derived from feldspar and silica. So fel and from silica, that gives you felsic. In addition to quartz and feldspar, most granitic rocks contain about 10% dark silicate minerals, usually biotite mica and amphibole. So you can see here some of these contain a little bit of dark material, namely biotite and the amphiboles. Rocks of granitic composition include granite and rhyolite. So you can see there's two forms of this. So if it's got a coarse-grained texture, which we'll talk about soon, you can see it as granite, or if it's more fine-grained, it's rhyolite. Rocks that contain at least 45% dark silicate minerals and calcium-rich plagioclase feldspar but no quartz are said to have a basaltic composition. Basaltic rocks contain a high percentage of dark silicate minerals, so geologists often refer to them as being mafic, that is from magnesium, and ferrum, the Latin word for iron. So you combine ferrum with magnesium and you get the mafic. So here we're looking at the third column where we have basaltic. These are mostly dark minerals now, at least 45%, and so they're darker in color. Because of their high iron content, they're darker and denser than granitic rocks. Rocks of basaltic composition include basalt and gabbro. They make up the ocean floor as well as many of the volcanic islands located within ocean basins. Rocks with a composition between granitic and basaltic are said to have an andesitic composition or intermediate composition, after the common volcanic rock andesite. Intermediate rocks contain at least 25% dark silicate minerals, mainly amphibole, pyroxene, and biotite mica, with the other dominant minerals being plagioclase feldspar. This important category of igneous rock is associated with volcanic activity that is typically confined to the seaward margins of the continents and on volcanic island arcs such as the Aleutian Chain off the coast of Alaska. At the far end of the compositional spectrum, on the far right of the image, is the ultramafic igneous rock group, composed almost entirely of dense ferromagnesium minerals. And again, ferromagnesium just combines iron and magnesium. Although ultramafic rocks are rare at Earth's surface, the rock's periodite, which is composed mostly of the minerals olivine and pyroxene, is the main constituent of Earth's upper mantle. So this can be an intimidating graphic to look at in the beginning, but just note it's breaking things down by how much light and dark minerals they have. So here it's almost all light minerals, so we're going to get a light colored rock, either granite or rhyolite, and on the far end we'll get the darker minerals, like periodite and comatite. And on the bottom here it just shows you arrows and showing silica content, how much potassium, sodium, iron, magnesium, calcium, so on, and we'll talk more about the temperature at which they're melting begins soon. So if you want a better look at this chart and a better demonstration of how it works, I will recommend you take a look at this video. So pause the video here, take a look at the YouTube description, or type this link into your address bar, and just watch the few-minute video helping to break down this chart a little bit more. Okay, moving on. Texture is the size, shape, and distribution of the particles that collectively constitute a rock. Texture is an important property because it allows geologists to make inferences about a rock's origin, based on careful observations of crystal size and other characteristics. As we mentioned, rapid cooling produces small crystals, whereas very slow cooling produces much larger ones. As you might expect, the rate of cooling is slow in magma chambers that lie deep within Earth's crust, whereas a thin layer of lava extruded on Earth's surface may chill to form solid rock in a matter of hours. Small molten blobs ejected from a volcano during a violent eruption can solidify in mid-air. So we see a variety of textures in our igneous rocks based on the timeline or the time needed to cool. So the faster the cooling, the smaller the grains, the slower the cooling, the bigger the grains. And you can see this very clearly. Here we see slow cooling, so very coarse-grained, very rapid cooling when we have an eruption, so we see almost no grains at all. So let's go ahead and step through each of these textures with some samples of different rocks. Igneous rocks that form at Earth's surface or as small intrusive masses within the Earth's upper crust, where cooling is relatively rapid, exhibit a fine-grained texture. By definition, the crystals that make up fine-grained igneous rocks are so small that individual minerals cannot be distinguished only with the unaided eye. In other words, you'll need a microscope or other sophisticated technique to see the individual grains. Therefore, we commonly characterize fine-grained mineral rocks as being light, intermediate, or dark in color. So here we have three examples: rhyolite, andesite, and basalt. All of these have different compositions, so you can see the lighter composition and the darkers, but you can tell that they all have a very fine-grained texture. You can't see individual minerals inside of them. They're fairly smooth in that sense. So their crystal sizes are very small, indicating that they cooled very rapidly. On the other hand, when larger masses of magma slowly crystallize at great depth in the Earth, they form igneous rocks that exhibit a coarse-grained texture. Coarse-grained rocks consist of a mass of intergrown crystals that are roughly equal in size and large enough so that the individual minerals can be identified without the aid of a microscope. Geologists often use a small magnifying lens to aid in the identifying of minerals in these coarse-grained igneous rocks. So for example, we have diorite, granite, very common, especially in like tabletops, and gabbro. Well, sometimes we have a mix of both. A large mass of magma may require thousands or even millions of years to solidify. Because different minerals crystallize under different conditions of temperature and pressure, it is possible for crystals of one mineral to become quite large before others even begin to form. If molten rock containing some large crystals erupts or otherwise moves to a cooler location, the remaining liquid portion of the lava will cool more quickly. The resulting rock, which has large crystals embedded in a matrix of smaller crystals, is said to have a porphyritic texture. The large crystals in porphyritic rocks are referred to as phenocrysts, whereas the small matrix of other crystals is called the ground mass. Many extrusive rocks exhibit voids that represent gas bubbles that formed as the lava solidified. These nearly spherical openings are called vesicles, and the rocks that contain them are said to have a vesicular texture. Rocks that exhibit a vesicular texture often form in the upper zone of a lava flow, where cooling occurs rapidly enough to preserve the openings produced by the expanding gas bubbles. Another common vesicular rock, called pumice, forms when silica-rich lava is ejected during an explosive eruption. So at this point, I think I have a fairly interesting video that you can watch on a recent Hawaii lava flow. So you can actually see an image or video very similar to this lava flow here. So it's not that informative in terms of lecture content, but it's very interesting to see, especially firsthand. During some volcanic eruptions, molten rock is ejected into the atmosphere, where it is quenched and becomes a solid rock. Rapid cooling of this type may generate rocks having a glassy-like texture. Glass results when unordered ions are frozen in place before they are able to unite into an orderly crystalline structure. Obsidian, a common type of natural glass, is similar in appearance to dark chunks of manufactured glass. And I apologize if you hear weird sounds in the background. My dog is sneezing and being a punk right now, so my apologies. Another group of igneous rocks is formed from the consolidation of individual rock fragments ejected during explosive volcanic eruptions. The ejected particles might be very fine ash, molten blobs, or large angular blocks torn from the walls of a vent during an eruption. Igneous rocks composed of these rock fragments are said to have a pyroclastic texture or fragmental texture. A common type of pyroclastic rock, called welded tuff, is composed of fine fragments of glass that remained hot enough to eventually fuse together. So here we have a chart that kind of basically classifies all of our igneous rocks. And if you're in my actual course, you will be using this in lab to identify rocks. Geologists classify igneous rocks by their texture and mineral composition. The texture of an igneous rock is mainly a result of its cooling history, whereas its mineral composition is largely a result of the chemical makeup of its parent magma. So here again we see the 4 mineral composition groups, and then all of the different rocks that we've talked about, plus some others, categorized by their texture on the left and their color on the bottom. So let's discuss some of the common granitic rocks. Granite is a coarse-grained, intrusive igneous rock that forms where large masses of silica-rich magmas slowly solidify at depth. Episodes of mountain building may uplift granite and related intrusive rocks, with the processes of weathering and erosion stripping away the outer-lying crust. Areas where large quantities of granite are exposed at the surface include Pikes Peak in the Rockies, Mount Rushmore in the Black Hills, Stone Mountain in Georgia, and Yosemite National Park in the Sierra Nevada. Rhyolite is the extrusive equivalent of granite, and likewise is composed essentially of light-colored silicate minerals. This fact accounts for its color, which is usually a pink to light gray. Rhyolite is fine-grained and frequently contains glass fragments and voids, indicating its rapid cooling in a surface environment. In contrast to granite, which is widely distributed as large intrusive masses, rhyolite deposits are less common and generally less voluminous. Yellowstone Park is one well-known exception where extrusive rhyolite lava flows are found. Obsidian is a common type of volcanic glass. Although dark in color, obsidian usually has a felsic composition. Its color results from small amounts of metallic ions in an otherwise clear, glassy substance. Because of its excellent conchoidal fracturing and ability to hold a sharp, hard edge, obsidian was a prized material from which Native Americans chipped arrowheads and cutting tools. Another silica-rich volcanic rock that exhibits a glassy and also vesicular texture is pumice. Often found with obsidian, pumice forms when large amounts of gas escape from a molten rock to generate a gray, frothy mass. In some samples, the vesicles are quite noticeable, whereas in others, the pumice resembles fine shards of intertwined glass. Because of the large volume of air-filled voids that are contained within pumice, most samples of it will float in water. Andesite is a medium gray extrusive rock. It may be fine-grained or it may have a porphyritic texture, often with phenocrysts or plagioclase feldspar, or amphibole. Andesite is a major constituent of many of the volcanoes that are found around the Pacific Rim, including those of the Andes Mountains and the Cascade Range. Diorite, the intrusive equivalent of andesite, is a coarse-grained rock that resembles gray granite. However, it can be distinguished from granite because it contains few or no visible quartz crystals and has a higher percentage of dark silicate minerals. The most common extrusive igneous rock is basalt, a very dark green to black, fine-grained volcanic rock composed primarily of pyroxene, olivine, and plagioclase feldspar. Many volcanic islands, such as the Hawaiian Islands and Iceland, are composed mainly of basalt. Furthermore, the upper layers of the oceanic crust consist of basalt. In the United States, large portions of Central Oregon and Washington were the sites of extrusive basaltic outpourings. The coarse-grained, intrusive equivalent of basalt is gabbro. Gabbro is not commonly exposed at the surface, but it does make up a significant percentage of the oceanic crust. Because igneous rocks exhibit a wide range of compositions, it is logical to assume that they originate from equally diverse magmas. However, geologists have observed that a single volcano, fed by a single magma chamber, may extrude lavas exhibiting quite different compositions. To explore this idea, a pioneering investigation into the crystallization of magma was carried out by N.L. Bowen in the first quarter of the 20th century. Bowen demonstrated that magma, with its complex chemistry, crystallizes over a temperature range of at least 360 degrees Fahrenheit. Unlike liquids that consist of just a single component, such as water, which solidify at a specific temperatures. As magma cools, certain minerals crystallize first at relatively high temperatures. At successively lower temperatures, other minerals begin to crystallize. This succession of minerals became known as Bowen's reaction series. The first mineral to crystallize from a body of magma is olivine. Further, cooling results in the formation of pyroxene as well as plagioclase feldspar. At intermediate temperatures, the mineral of amphibole and the mineral biotite begin to crystallize. During the last stage of crystallization, after most of the magma has solidified, the minerals muscovite and potassium feldspar may form. Finally, quartz crystallizes from any remaining liquid. Olivine and quartz are not found in the same igneous rocks because quartz crystallizes at such a lower temperature than olivine. Analysis of igneous rocks provides evidence that this crystallization model approximates what can happen in nature. In particular, we find that minerals that form in the same general range of Bowen's reaction series are found together in the same igneous rocks. For example, the minerals quartz, potassium feldspar, and muscovite are located in the same region of Bowen's diagram, and are typically found together as major constituents of the igneous rock granite. So, how can a single volcano, fed from a single magma chamber, form rocks of quite different compositions over its lifetime? Well, first, as Bowen demonstrated, different minerals crystallize from different magmas according to a predictable pattern. As each mineral forms, it selectively removes certain elements from the melt. For example, crystallization of olivine and pyroxene, the first two that solidify, selectively removes both iron and magnesium, leaving the remaining melt more felsic. If some mechanism then physically separates these crystals from the remaining melt crystallizes to form a different, more felsic rock type. One such mechanism is crystal settling. If early formed crystals are more dense and heavier than the remaining melt, they will tend to sink toward the bottom of the magma chamber. Consequently, the lower and upper parts of the magma chamber form rocks of different compositions. The formation of one or more secondary magmas from a single parent magma is what is called magmatic differentiation. At any stage in the evolution of magma, the solid and liquid components can separate into two chemically distinct units. Furthermore, magmatic differentiation within the secondary magma can generate other chemically distinct masses of molten rock. Consequently, magmatic differentiation and separation of the solid and liquid components at various stages can produce several chemically diverse magmas and ultimately a variety of igneous rock. So at this point, we'll finish up our lecture with a few questions. So remember, for these, just pause the video when you're looking at this slide or the question slide, and then I'll give the answer when you're ready. So number 1, blank rocks always originate at the surface of the solid earth. Well, at the surface, we're talking about sedimentary rocks. More on those in the next lecture. Question 2. Which one of the following statements is not correct? Okay, well, the statement B, sedimentary rocks may weather to igneous rocks. Well, that is not correct. Weathering of rocks produces sediment, but cannot produce igneous rocks. Question 3. Intrusive igneous rocks are often characterized as coarse-grained because what? Well, because they cool slowly at depth, allowing larger crystals to grow. So intrusive igneous rocks cool slowly at depth, and that gives them their coarse-grained texture. Question 4. All igneous rocks have blank. Okay, the answer here is B, a solid mass of interlocking crystals. When a magma body cools, over time the liquid melt is transformed into a solid mass of, again, interlocking crystals. 5. Generally speaking, which of the following is correct? Okay, the answer here is C. Felsic rocks are light in color. They're dominated by the light-colored silicates such as quartz and potassium feldspar. And last but not least, question 6. What kind of texture is shown here? Okay, in this case, we're talking about porphyritic texture. So this is whenever you have two different rock sizes or texture sizes. We have the phenocrysts, the larger pieces, and then the ground mass, the smaller pieces. All right, so that's it for our igneous rocks. In the next 2 lectures, we'll discuss the other types of rocks. As always, thanks for watching and have a great day.